Howdy, folks. I'm Tom Coughlin,
I'm Jim Handy.
and we've often given some talks together at SNIA events, for instance, the January event, and we get a chance to do it again. I want to thank SNIA and the Storage Developers Conference for giving the opportunity to talk with you folks. And we're going to talk about the memories of tomorrow.
So Tom and I are both industry analysts. One of the things that we have to do for a living is to forecast the future, and usually we go out like 5 years, some cases only 1 year. But we thought, this is an opportunity to really talk about things far out in the future. And Tom's got a couple of sons in college. I've got kids who are just out of college. We were thinking about what are things going to be like for them way out there. So we said, let's say 2075, pretty far out in the future. Tom's a big science fiction aficionado, likes all the Star Trek and stuff like that. And, so we put our heads together and we said, what is life going to be like for our kids out, that far away towards the end of this century?
So there we are.
That would be our kids. They'd be about 80. And they're doing the same thing that old people do today. But something that I wanted to talk about really here was what are driving forces behind this. And so we're going to be talking a lot about driving forces. This is a driving force in memories. This is something that has been going on for a long time. If you look across the bottom of this chart, you'll see that it's got process geometries, and it goes kind of backwards. The smaller process geometries are off to your right-hand side. And costs per gigabyte, which is on that log scale on the vertical axis, that represents what the cost per gigabyte would be for flash memory, which is the red line, and for some alternative memory, which is the black line. This is the thing that's been driving investment in alternative memory technologies, or now they're called emerging memory technologies, for the past 30 years or so, is that people have seen that there's going to be a crossing between these two lines. You'll notice the red line goes down. That's according to Moore's law. That's what is the cost to manufacture a byte of flash memory. And you'll notice that all of a sudden it just stops going down. It just kind of goes level. And that's where you reach what's called the scaling limit. For years, people have known that DRAM and NAND flash, or actually it was just flash in general, were going to hit a scaling limit. In the 1990s, I hired a guy from Intel who was hired into Intel, into the flash memory group from Western Digital in the 1980s, because Intel knew that disk was going to do something like this and that NOR flash was going to take over the world. That didn't happen, but there have been a lot of junctures where people think this is going to happen. 3D NAND right now is because planar NAND has hit a scaling limit, and so 3D NAND was a way of working around it. But these other memory technologies, the thing that they've got going against them, and I'll talk about this a little bit more later on, is that it costs more to process a wafer. And so because of that, you've got the black line higher than the red line on the chart. That shows that you've got a higher cost per gigabyte, which is what's keeping these memories from actually taking over the rest of the market. They're too expensive. But once they get to a point where they can scale past NAND flash, and I'm sorry, I didn't put that down. So when scaling stops, then the costs stagnate. Anytime that the higher price technology can scale past NAND and can get to smaller, or past an entrenched technology and get to a smaller process geometry, then that's going to allow it to get to a lower cost, and cost is everything when it comes to memories. And so that's why people have been investing in MRAM, resistive RAM, ferroelectrics, any carbon nanotubes, any of those things. And the thing is that the scaling limit has been on us for years. The first time I heard about scaling limits was probably 1980, maybe 1981, when there were worries that we weren't going to be able to get past 7 nanometers. 7 microns. Today, everybody's very easily talking about 7 nanometers and how we're going to be able to do that. This is 1,000 times smaller. So, you've got the new memories. Their intent is to extend scaling to keep us on Moore's law. And the technologies we have today, flash and DRAM, can't scale. The new technologies all can scale past flash and DRAM. I say they can't scale. Flash has gone off to 3D, and so that's going to go for a while. DRAM, they keep finding new ways to do it because everybody in this valley is a super genius and seems to be able to just figure out ways to do it. But all of these other technologies have been sitting there just waiting for their opportunity to come in. There's resistive RAM, MRAM, PCM, ferroelectric memories, conductive bridge RAMs, and NRAM is carbon nanotubes. But there's something else that people haven't really talked about with these new memories, and that is that they're non-volatile. And so that's why there's so much work right now going on in SNIA for persistent memory, is because it's out there. You know, it's really going to happen. But also, something really nasty about today's non-volatile memories, NAND flash, is that you have to do block erases and page writes, and so you can't modify individual bits. You also have to pre-erase them. So, you know, these new memories don't need either one of those things. They're also significantly faster than flash. Flash has a certain thing that it has to do, part of the erase and the program mechanism, which just can't be sped up over time. And then finally, because of the fact that they've got no refresh like DRAM has, then they're lower power, and so they look like a good candidate to replace DRAM. And then, as that prior slide showed, if we get the scaling right and everything else hits a wall, then we'll be able to get these memories for cheaper. So they're all really wonderful things. And that's what's brought us storage class memory. The idea of storage class memory was actually conceived at IBM probably about 15 years ago. They said, all these things have been being developed for a long time. How are they going to impact computer architecture? And so IBM's been thinking for a very long time about how can they develop software that will take advantage of this in the future. IBM actually put together a definition, which I'm going to painstakingly read to you. So storage class memory combines the benefits of solid-state memory, such as high performance and robustness, with the archival capabilities and low cost of conventional hard disk magnetic storage. Now, if we pull that apart, there are actually only 4 statements in there. The first one is that it has to be high performance. It's got to be memory. It can't be storage. So NAND flash doesn't do that. It's got to have archival capabilities. Maybe I'm reading this too loosely, but I say that just means persistence. But what we seem to be ready to abandon with what we're doing right now is we're getting rid of the robustness of hard drives. We're okay with things that don't wear quite as well as a hard drive does. And we're also not looking for things that cost as little as a hard drive does, because we've found out since that time that there are ways to fit things into the memory storage hierarchy that are more expensive than a hard disk drive. Well, you know, you look at that, you say, that kind of looks familiar if you're as old as I am, you know, somebody with gray hair, because that's just core memory. So I'll pass it over to Tom, and he can talk a little bit more about that.
Thank you much, Jim.
You get to wander the stage. You've got the remote.
I do have the remote, yes. Amazing power. So I've had the honor of being a member of the IEEE, doing some things in it, among which is being participant in the IEEE Future Directions Committee under technical activities. And one of the activities they've had going on the last few years is the Rebooting Computing Initiative. Now, IEEE is the largest technical organization in the world, and they've got a lot of different disciplines involved, a lot of societies and things. I'll show you people that are involved in this. But the whole idea here was, as Moore's law, the traditional scaling algorithms we've been using, or scaling rates we've been using in order to advance semiconductor technology slows down, we've got to rethink what are approaches to be able to handle the huge amounts of data that we're going to have to process. You know, some of the pundits have said 163 zettabytes of data created per year by 2025. That's the latest IDC thing. So how are we going to use that data? How are we going to understand it? So we've got to rethink everything. And we have to go back all the way, looking back even to the roots of computing, back to Turing and von Neumann. Okay? And IEEE is kind of a natural one. And the reason why is because the whole computing stack, all the different things that are involved in computing, from devices through the compute architecture into the software, are part of IEEE. So here's an example of the societies that have been involved in this Rebooting Computing initiative: solid-state circuits, computers, circuits and systems, nanotechnology, Council on Superconductivity, Electron Devices, Society of Reliability, Council on Electronic Design Automation, IEEE Magnetics, among other groups have been involved in this. So, and the slides here I'm going to show, by the way, are from Tom Conti, who is the co-chair of the IEEE Rebooting Computing Initiative, and also a professor at Georgia Tech and a former president of the Computer Society. So we're going to take a look. This is this look from this rebooting computing, sort of a given idea, a context for how memory and storage is going to fit into future computing architectures, which are going to drive consumer electronics, client devices, and enterprise in the future. And we're going to look at the different applications. We're going to first of all look at the whole computing stack. I'm going to show you that in just a minute here. In fact, that's it there, going all the way from the bottom where we have the device level into the general computer hardware architectures, then up into the software at the top of it here. And we're going to look at different approaches and a few different approaches and look at the level of disruption of this computing stack that each of these approaches would entail. And so at the legend here at the bottom we see, it's down at the bottom there for those you may not be able to see it very well, going from a light color, the white color, to a deeper red. There's a more and more level of disruption as we move from the light to that red color. So we're going to take a look at first what's called Moore's More, okay? And as you can see here, we're going to have a lot of disruption that occurs in this, but it's basically going to be at the device level, at the storage memory device level. It's not going to impact so much the general computer architectures. It's not going to impact the way that we do algorithms to process information, okay? And let's, and the other one is what we call hidden changes, okay? Now, hidden changes is where it starts to move up into the hardware stack, higher up the hardware stack of computers, but it doesn't impact the software very much yet. Okay, so there's very little disruption on the upper level of the compute stack. The next one, this third level, is where we're calling what we're calling architectural changes, where we're actually starting to impact the whole computer stack, particularly on the lower levels, but also having some impact now on going all the way up into the software. And then finally, this fourth level, which is a non-von Neumann computer architecture. In other words, we're not doing anything like we've ever done it before, you know, for decades now. So we have to rethink everything. So these are these four different levels of disruptive approaches that we're going to go through. And we'll tie that back into why that's important in terms of storage and memory. First of all, let's look at Moore's More. More. Okay, so more. It's the traditional continue the scaling as far as we can go, maybe 7 nanometers now, you know, with those big FinFETs, 3D NAND, so we move into 3D stacked architecture, which can probably go to hundreds of layers potentially. New switches, unreliable switches, you know, pre-threshold or close to threshold type logic devices, and into non-silicon type devices, some of which the people are out here in the exhibits here, things like MRAM. Okay, where we're actually using the spin of electrons in order to be able to store information, potentially even in the future, perhaps even to process information. But that's part of these higher level architectures. Phase change memories, where we're using physical change in the state of a solid state device in order to change the resistance of that device and therefore be a memory device. Memristors and various types of resistive RAM devices where we're causing a change in resistance to be in form of memory, and then things like ferroelectric memory and different devices like that. So we're at the device level. We're changing what we're doing it with. We're not changing what we're doing yet. Okay, so that's this Moore's More approach. Let's look at this next level, what we're calling hidden changes. Now again, in hidden changes, we're starting to impact some of the lower levels of a computer stack. But they don't change the instruction set yet. They don't change the instruction set, and therefore they don't also have a huge impact on the software, how we're doing the software yet. So their devices there, for instance, include changes in the devices, include some logic level changes in functional units, in the microarchitecture of these devices. Context switch issue fits in here, and Jim will be talking about that a little bit later on. Microarchitectural support for non-deterministic logic devices, things like adiabatic computing or approximate computing technologies, things like that. But there's no significant impact on basically what memory and storage is necessarily, except for the device level. Next, we're getting into this architectural changes. So now we're getting into further levels of disruption. Sorry, maybe it's destruction. Yes, that will start to impact the whole architecture to some extent of computing. Now, these architectural changes beyond x86 type computing, examples of this are things that are moving into special purpose computing devices, which actually have to have some changes in the software, like CUDA with GPUs, FPGAs, things of that sort. So it's things, this is again where we're getting into the whole memory approach, moving computation to the data. In fact, at an event associated with the Mobile World Congress up in San Francisco yesterday, it was interesting, there was some speculation, Micron folks who were talking to, that actually the energy used to move the data around, to bring it to computers, is a significant component in the total energy budget. Something that, if we could change that, we could change, the power budget that we have in a lot of devices and make, for instance, these mobile devices last a lot longer. So in-memory computing, in situ processing examples, special purpose computing like the GPUs used for image processing, also now being repurposed for artificial intelligence and other capabilities, but it requires some new programming in order to program these special processors for these special applications. Now the final level is where we're going beyond von Neumann, beyond the computer architectures we've used since virtually the beginning of computing. These involve things like quantum computing. We're using things called qubits, for instance, to process information, and it's more than just single, 1 zeros that you can do very complex processing. In fact, this stuff is so new that the IEEE standards group, activity last week said that they formed a group to define terminology around quantum computing. Things like neuromorphic computing. We're trying to create computing that emulates the way that our brains work to process information. Our brains actually do an awful lot for rather a low amount of power. It's something that our current processing capabilities aren't able to do, and we can do interesting cognitive and contextual things that modern machines can't do yet. Return of some kind of analog computing technologies. Now, all these are very exciting things. There's a lot of investment. There's startups involved in this. There's big companies putting research into this, but it's also very immature, and it's probably going to be a bit further away before we see these huge architectural changes, and they will take a while in order to create. Now, in addition to these changes in computing, we've got huge amounts of data we're going to be generating for various things. We're from going to 4K, 8K video, to genomic research, big science, to future medicine, things of that sort. All the Internet of Things related activities, voice image recognition, autonomous vehicles, cybersecurity, industrial automation. There's a whole level of stuff that's going to drive that. Those estimates of like 163 zettabytes of data created per year by 2025. We're going to have the means of processing this stuff, of running sophisticated algorithms, for instance, those often called artificial intelligence, in order to be able to make meaning out of all of this unstructured data, this data that you have to pull references out of the data itself in order to understand it, in order to be able to use it. So this stuff is going to require changes in our storage and memory, and so I'm going to turn it back to Jim, who's going to talk a bit more about that.
Yeah, there's one of those things that isn't going to go away is your jobs, I guess, too.
Good
but
to know.
There are two major problem areas in memory today, and that is that memory loses its data and that storage is slow. And I'm going to address these actually in the reverse order which they've got. But that's the whole virtual memory system, caching, tiering, all of that is worked around these. So what do you do about latency? And there is a lot of talk today about moving compute close to the data. And then the other is to use lower latency storage. I'll get into some detail on these in a bit. But then, what do you do about the non-volatility? The old way was just to make a number of verified copies to storage. And so hopefully you had fast storage, because every time you went out to put something onto storage, then you'd end up incurring a huge penalty with hard drives and a lesser penalty with solid state drives, but it's still slow. The new way that SNIA is doing an awful lot of championing on today is to make the memory persistent. It used to be that there were systems that you could buy that were just wretchedly expensive, that were just big DRAMs with car batteries in them. And those worked for a while, but then around 2009, then people started putting together NVDIMMs with flash backups. And now we've got these new persistent memory or storage class memories that I was talking about earlier. Those are moving in there. And so with each one of these, you get not only higher speed, but also better economics. The persistent memory is a good solution to this thing. It's going to come to you in the form of an NVDIMM, and Intel is already beating on the drum for this with their Optane initiative using a 3D cross-point memory. But the other emerging memories are also going to get in there. Intel is just motivated to make this happen because they believe that it's an important part to realizing the full speed of the processors that they have. And so they're using this as a way of enabling the ecosystem to make their processors sell better. But there are some issues that come up that we're going to talk about, and that is context switches, cost, maturity, and software support. SNIA will be very big into that last. But today we've got NVDIMMs, which are serving as a very useful platform for prototyping for all of this. Your NVDIMMs, NVDIMM-N is what I'm showing here, and I think this is in a Giga one. This actually has the DRAMs on the one side of the module, and that's the side that's kind of below. So there are 8 DRAM chips on that. And then the other side has a NAND flash chip because NAND is a denser chip than DRAM is, so you can get more bits into the fewer number of packages. And then a microcontroller that shuffles everything around. What I don't show with this is a supercapacitor that's needed to keep the DRAM alive during the time that you're moving the data around. But also, we're going to be moving to persistent memory technologies. And this is just kind of a further illustration of something that I said before. And I'm not going to walk you through all the details of this, but instead just you look across the top. That's all of current memory technologies. You look down the left-hand side, it shows you a lot of attributes to those technologies, whether it's volatile, what kind of power it consumes. And then I've done just kind of a good, bad, and so-so marking of these things with greens and reds. The real thing, the takeaway from this is to look at all these current memories and say how much red is on there. Some of them are too expensive, so they're red along the bottom. Some of them are volatile, SRAM and DRAM. So up in the corner, you've got these red boxes up there. But all of them seem to have some kind of a blemish. You go to the new memories, and all of a sudden there's a whole lot of green. And that's because they're fast, they're non-volatile, they don't consume an awful lot of power. They are just all sweetness and light until you get down to the bottom line. And then it's, what is the cost? And today the cost for these is very high. And it's going to take a lot of volume to move through the machine to make the costs of these go down. And so that's the thing that's really been standing in their way. Also, that scaling limit thing that I showed in the very first graphic slide, that also explains, a lot that way. So we've got that working, but then we've got another solution that people are talking about an awful lot, and that's bringing compute to storage. So in situ processing, we've got these things that happened in the past. Kinetic and the WD Labs microserver were early trials for this, but also we've got some companies today, NGD, NVXL, and ScaleFlux, and I noticed Thad Omura from ScaleFlux is here today. So they're all working to put together SSDs that have good processing inside. And that's something for those of you who listened to the Microsoft talk yesterday morning, you would have heard an awful lot about the benefits of that. But there was also some talk in the, I'm trying to remember the name of the company that presented with Xilinx. Missing Link Electronics, MLE. Yeah, and they were also talking about how embedding processing in there. This is the next thing. Today we're talking about persistent memory. Tomorrow we'll be talking about in situ processing. But there are also places where that's being done not in the storage. And so I've got compute in memory. A couple of examples of that are the Tommy processor and the Automata processor. And I'll talk a little bit about why that's failed, because it might draw a parallel to some of the stuff that's gone in here. And then we have a similar thing that was tried a while ago, and it seemed like those didn't work, and I'm not positive as to why, and that is these things from Schooner, Virident, and Violin. So I'll talk a bit about those. First of all, though, in situ processing, I thought this was a nice slide that Intel showed way back in 2013, I think it was. I'm sorry, Micron.
Yes.
Shame on me. The reason I said that was because it was Ed Dollar who defected from Intel and went to Micron, and I still have it stuck in my mind that he's Intel. He's not even at Micron any longer. But he did this really cool presentation at the Flash Memory Summit where Micron had taken standard SSDs and had reprogrammed the processor inside and stuck a little tiny piece of MySQL into the SSD. And they were able to get something where the processing speed of the system scaled directly in proportion, this blue line, directly in proportion to the number of SSDs you added to the systems. If you wanted it to run 8 times as fast, you just added 8 SSDs. And the server that was running all these things rarely had anything to do because the SSDs were doing most of the sorts. Whereas that green line represents what would happen if you kept adding SSDs to a server. You know, the first SSD would just saturate the server's ability to do MySQL, and then you add SSDs and it doesn't really bring any performance increase. So, you know, that was a real eye-opener for me. But then you've got compute and memory. And I have to admit, I put this one on first because it's an old college friend of mine, Russell Fish, has his own company that puts together, it's put together an architecture of a DRAM with a processor in it. But they're not the only ones. Micron, once again, put together something called the automata processor. And that processor is designed also with, or that is actually a DRAM that's designed with a processor inside. And these have been designed to take advantage of incredible bandwidth that is available inside the DRAM chip, where all of the data is moving around in 4,000-bit wide or 8,000-bit wide buses. And it's able to solve certain problems that really drive people nuts. This is a nasty-looking diagram of network traffic that was something that was very easy to solve using the automata processor, but was something that would have been very difficult to do on a conventional server. So I think I hand it to you from here.
I think so.
Yeah. So.
Oh, no, we got a plan.
Oh, yeah, I forgot about that.
Well, they're coming up.
I was going to do. Yeah, okay. So these are the appliances that I promised to talk about a couple of slides ago. So Schooner Information System, which was later bought by SanDisk, they came out with something that was a box full of flash that would perform MySQL natively, and you'd just hand it commands and it would run on its own database. And it also could be programmed to do a memcached appliance. It came with both of those in there. At about the same time, Virident came out with something that was very much like that. Virident was later bought by HGST. So, those were two examples of places where companies tried bringing out dedicated appliances, which kind of do the same thing as these memories and the in-situ processes. There was another one, Violin Memory, that came out with a Microsoft Windows server that was in there. Now, neither the DRAM chips with a processor in them nor these have fared very well. I know with the DRAM that has the thing inside that it goes against something that DRAM manufacturers thrive at, and that is they crank out tens of millions or hundreds of millions of identical chips without any variation in their factories. Once you ask them to make 1,000 of something, then the cost goes up by several orders of magnitude. And so that's something that has worked very much against them. I can't say that that's the same thing that caused the failure of these systems like the Violin, Virident, or Schooner systems, but it's perhaps some similar kind of an economic thing.
So if we're going to be carrying on this kind of integration, of storage and memory, storage and memory, but also trying to get the processing closer to the actual data, there's a lot of things that are required throughout the system: software support, changes in BIOS, CPU, perhaps even new pins in the bus. And one thing there's been stuff that's been going on in SNIA, especially the solid-state storage initiative, which, by the way, I took a look. It was founded in 2008. So next year, speaking of anniversaries, this will be the 10th. Next year will be the 10th anniversary in September of the Solid State Storage Initiative. And so I've had a pleasure being part of that group since it was founded. And we're moving, as we take a look at moving away from non-volatile memory, it has more and more characteristics of storage. We can start to treat things where we have used storage before, instead take a memory-centric approach to it. We can store, for instance, at the byte level versus at the block. We can avoid the traditional storage stacks. We can avoid things like flash translation because we don't have to translate. We can just deal with the native characteristics of flash and not have it act like a hard disk drive. So there's important things this allows, and the SNIA Solid State Storage Initiative has had this model of this programming model for this, where they're basically looking at, we have these persistent memory devices at the bottom here. We've got drivers that can operate and allow us to file system access this or kernel. But what really is sort of the holy grail eventually is where we show the application, instead of going through, say, a file system, where it can directly access the memory, the way that it happens inside the processor itself, where a lot of the working memory, working storage effectively is memory and acts like memory. And so that's where you have that direct interaction between the application and the persistent memory. And that's where we're going to be, a lot of things are going to be heading to in the next few years. So in order to do this, this is yours again, I think. Well, I'll do this. So again, we need BIOS support, current BIOS, DRAM can corrupt at boot. What do we do when, your data doesn't go away at boot? You want to do it? Okay.
Yeah. So Tom talked about the software needs to support persistent memory, but there are other needs. There are also BIOS needs, and there are also processor needs. And so what we have here is a list of how the way the current BIOS looks at memory and the way that the persistent memory BIOS needs to look at the memory. That the current BIOS says DRAM's corrupt at power on. The permanent memory BIOS has to understand whether or not the DRAM's got valid data in it at power on, because it could be valid, it might not be valid, so there has to be a protocol for that. Power fail in current BIOS, you just say, okay, that's it, game's up. The memory's gone, the register's gone, the cache is gone. With the permanent memory BIOS, everything has been pushed into the DRAM. The memory buffers have been moved in there. The memory itself is moved in. The registers are pushed in if there's enough power in the system to do that. And maybe even the dirty lines of the cache. There are ways of doing that. And so, that's all stuff that has to be managed at the BIOS level. And that's something that the people who have been doing persistent memory have been working with software companies with for a long time. But also, persistent memory needs processor support. So we've got the software support Tom talked about, the BIOS support, the processor support. Intel has put new instructions in their architecture that they just announced about a year ago, where there's a cache and write, cache flushes are handled separately, but there's a write buffer flush command, where when that command is invoked, then anything that is waiting to be written is pushed into the memory so that it can be taken into persistent memory. But also, and I'm not sure that I understand the architecture well enough to know why this is important, they decided that rather than wait for a power failure to move the NVDIMM data from the DRAM into the flash memory, they instead just, they have an instruction that tells the NVDIMM to do that. But then you've got this other issue that's a context switch issue that is another place where the processor needs to take care of this. And I just prettied up a diagram that Doug Voigt put together, I think it was him, that shows how the speed of different technologies, storage technologies, works with the latency of there. And so with hard drives, SATA SSDs, and NVMe flash, all of those are things that can be satisfied through an interrupt-driven architecture. And so that's what that big blue box at the top is. It's okay to do interrupts. Then you've got a zone that is kind of, you don't know whether it's faster to do an interrupt because an interrupt takes a long time to do the context switch, or whether you'd rather just have the processor go into an idle loop and pull a flag. And persistent memory, unfortunately, largely falls into that questionable area. And so maybe the processor is going to have to change so that those context switches happen faster, or maybe software is just going to have to be written to pull the persistent memory. So it's back to you.
It is, and I'll do the final stretch here. But this is similar to the advent of SSDs. New software is required. We had to get in new approaches for caching and tiering. It was part of what led to software-defined storage activities, particularly where we're integrating flash as the primary storage, faster I/O stacks, new hardware, and interfaces as well, including the NVMe and now potentially even NVMe over fabrics. So we'll need similar efforts in order to make these things happen, to develop this in situ or memory-centric computing. And we'll have to do that to make this work with compute and memory virtualization, future approaches for virtualization where we have lower latencies to deal with. Could be really interesting. So in summary, there's a lot of things that are going to change. There's huge demand to be able to process mountains of data. And we're going to need new computer architectures and memory technologies, especially persistent memory technologies, that are going to be able to support this. We're going to need to bring processing to the storage in order to save power, in order to save time. We're going to have new approaches to computing the way we do things, which ultimately could change the very structure of programming and of compute. So we'll have to have support in software, architecture, and hardware. And so I hope you've enjoyed this. If you want to hear more about storage for unstructured data after you've gotten done here with the Storage Developers Conference, Jim and I are both going to be involved in this Storage Visions Conference in October 16th here. So with that, we want to thank you very much. I don't think there's time for questions, but we'll be around if you want to ask us some things later. Thanks.